Dynamic logic. If you haven't played with it, I would recommend it. It's fun to get into, and the tools and the hardware are way less annoying than they used to be. Alright, so the Fpga is actually something I would totally recommend playing with if, even if you're new to FPGAs. There's this project called IceStorm. Oh, that's going to be difficult to Google for. If you search for IceStorm FPGA, you'll find this page. And there are a few related projects, but this will get you started. Basically, this is I think an amazing milestone. It's really the first viable open source FPGA toolchain. So, and if you haven't heard of FPGAs before, just really briefly, they're programmable hardware. So, a chip that has a sea of logic elements, so little lookup tables and wires and inputs and outputs that are just kind of ready for you to wire up in whatever way you want. And so this is a software tool chain that is based on really detailed reverse engineering of, in the image, in that binary image you give the FPGA, what do all those bits mean and how do they configure all the logic elements and the wires. So this was the work of a few people, but I think most notably Clifford Wolf. He was the one who did the reverse engineering and wrote the bitstream compiler and decompiler. And so the upshot of that is that it's by far, I think, the least annoying kind of entry-level FPGA toolchain to get involved with, because you don't need like a 3 GB download. You don't need to worry about license keys and installing Windows or maintaining something that expects like ancient Linux binaries. Like, this is something you can compile yourself, and if it doesn't work, you can hack it until it works or submit a patch or whatever. And it's especially nice because the FPGAs that it works with are pretty cheap, and you don't even have to build your own board because you can get like a dev board from the silicon vendor, this thing called the ICEstick, which I should just point the camera at since it's in a vise and I don't have one handy, but, oh, or actually since I have the computer here. Yeah, this is the thing. Do we have a picture? Yeah, this thing. So it looks like kind of a giant USB thumb drive, but it's, if you see that pricing, it is like under $30 including shipping. So I think it costs like $5 to get these shipped, but still, that is one of the cheapest FPGA development boards I've seen. And so something like this, plus these open source tools, actually make it pretty easy to get started with creating customizable hardware, which is really the only way that you can do this kind of thing, like taking a clock signal in at such a high frequency and turning it into something totally different and then outputting it again. Like, you could buy a dedicated chip that's designed to do that. Like, there's one from SI Labs, and in fact Adafruit has a breakout board for one version of that chip, but not the version of it that has like a clock input, which is what you need for this. So this was kind of a good solution in general, but also a good solution just for me given the parts that I had handy. All right, so it turns out this is actually all you need. Let me make clean and you can see how minuscule this really is. So 3 files for our hardware projects: a run-of-the-mill Unix makefile. This .v is the source code written in Verilog, and this .pcf file, which is named after the board that we're using, is actually just a really partial list of mappings between names in the source file and pin numbers on the chip. So that just tells us like how to plug this into the hardware. And we can take a look at each of these in a text editor. So these FPGAs that have been reverse engineered are pretty nice, and they're of course lower density and they don't have the features that you would find in, like a Xilinx or an Altera or something, Xilinx or Altera. But that's part of the reason they got reverse engineered, is because, you know, Clifford wanted to pick something that didn't have tons and tons of features, but was also, you know, also had reasons that you'd want to use it. So it is inexpensive and it's low power. So those are both pretty good pluses. And the toolchain also supports the larger variant of this. This is the HX1K or something like that, and there's also an HX8K. So this is all the source code we're dealing with, and a lot of this is just kind of not even especially necessary for the job. So I think I kind of want to talk about the toolchain first, though, just to get that out of the way before diving too much into the source. So you can actually get a pretty quick feel for the toolchain just by looking at the makefile rules. So we're starting with these Verilog files, and this .blif, I forget what that stands for, but it's a type of netlist format. So it's a representation of a bunch of electrical gates and how to connect them together, and that includes like abstract gates, like, you know, just ideal, you know, NOT and XOR, that kind of thing. Yeah, the makefiles for this toolchain are nice and clean too, especially like if you've ever tried to compile like with a Xilinx board in makefiles, especially if you've ever tried that running the tools in Wine, it gets pretty hairy. But the steps are actually pretty similar to if you've seen other FPGA toolchains. So there's one step that takes the really high-level description in Verilog and converts it to a logic description in this blif netlist file. And so that's just like, converts the kind of higher level like register transfer description that's in your Verilog code to just a sea of gates and how they're connected. Then the next step is this program Arachne place and route. Oh, I'm getting slightly ahead. So you do kind of have to know, if you're using this toolchain, that there are a few separate components, and they're in separate repositories that you have to like compile and install separately. It isn't like a single bundle yet. And that's partly because of kind of applicability, because these are each useful for different sets of, like, for example, these tools that start with ICE are part of the IceStorm repository, which is this kind of reverse engineering effort. And so the IceStorm tools are only relevant to this particular like ICE40 series of FPGAs by Lattice. But a lot of these tools are made to be general, so that once other FPGA series get reverse engineered, then with the addition of some new data files and some new features, the other tools could be made to work with those FPGAs, whereas like the packing tools and the timing analysis and the actual USB programming tool, like that's all going to be really vendor specific. So that's what these last steps are, just converting the ASCII description of the cells on the FPGA into the binary file that gets sent to the device, going back and figuring out how long all the delays are going to be in the finished design to make sure that it hits the timing requirements, and then actually copying the design to the board. Those are all the board-specific features that kind of IceStorm itself handles. But then these other two big steps, the synthesis step, where we're going from Verilog code to the gates, that's handled by this tool called Yosis, which is another whole big, like that's actually like by weight of code, by far the biggest thing here, because it's like a language compiler, you know, like any other language compiler, but it's for hardware instead of software. And so you can see here that it's this whole general purpose tool, but in this case there's actually like a script that's built in, or that comes with it, that does the synthesis like using the library of primitives that this FPGA expects. So it's kind of general purpose, but it also has to know like what it's mapping your Verilog code onto and like what it supports, and like it has to have libraries of primitives that it can take advantage of. And then this place and route tool called Arachne PNR is also designed to be pretty general. And it's taking all of those gates and trying to fit them into the physical resources available. So the matrix of logic elements, it has to figure out where things go and then how to use the interconnect to actually wire up the inputs and outputs. And so there's a lot of abstraction here, but the end result is really just ones and zeros. And so those get stored in memory. In this case, I don't actually have memory attached to this FPGA board, so I'm just sending it every time I start up the FPGA. So you could do that with another processor. You'd get this binary file from this toolchain, and then on a Raspberry Pi or an Arduino or anything else that can get the data there, you just send it basically like writing to an SPI peripheral, and that loads the ones and zeros into SRAM in the FPGA. And then those SRAM cells provide configuration data for all the internal routing and the lookup tables and all the other bits that the FPGA is actually made of. So what are we telling this to do? Well, just to kind of save the big one for last and get the IOs set, we don't have a lot of inputs and outputs here. This FPGA has a lot of pins that we could be using, but other than some LEDs, which are really just for debugging and for show, we just have the clock signals we're dealing with. In this case, we have an input clock from the chip whisperer, and then 2 output clocks going to the Ethernet and the microcontroller. So the Ethernet here is the ENC28J60 adapter. And these I've just picked to be mechanically convenient. This Pcf file is a pin constraint file, and normally you just use that to set the name of a signal and then what pin it goes to. But this is also where you would set like timing constraints. So if you want to make sure this is, so if I was going to tell the software like give me an error if this clock couldn't actually be safely driven to 30 megahertz, then that's the file I would put it in, and it would run those constraints for me. So now that I know kind of what the environment is, so we're compiling this thing with the synthesis library for the ICE40. We know we know where all of these inputs and outputs are connecting using the pin constraints. Then this is really the main function, basically, this top module for the Verilog code. And unlike software where we have a sequence of instructions, this isn't a sequence. It's just like a collection of things that all exist at the same time. So one of the things that exists on the FPGA is a phase-locked loop, which is basically a clock multiplier. It works by using an actual analog thing, so an oscillator that runs at a higher frequency that you can control. And then it controls that oscillator, kind of nudging it up and down to synchronize it with the clock that you're giving it using a feedback loop. So itself, it's kind of this little servo loop that's homing in on the right frequency. And these are parameters that mostly come from a little tool that comes with IceStorm that generates like divisors if you give it the frequencies you want. So I was like, I've got 30 megahertz coming in, 150 megahertz coming out, and it tells me what numbers to use for these parameters, which I think just add up to multiply it to, I think it's actually slightly more complicated than just a straight multiply by 5. It actually multiplies it up to a pretty high frequency, like 600 megahertz, and then divides it again because that's just, most PLLs are designed to have a stable internal oscillator that runs at a pretty high frequency like that. I don't actually know the analog reasons why that's more stable to operate at that high and then divide, but probably has to do with the magnitudes of the component values that you actually end up using in the circuit and the physical space available. So these things up here in the number, the kind of pound sign bracket, these are parameters for a block that we're instantiating. So just like this top module is, like a function in a computer language, a module is just kind of a unit of reusability. So because of the way that we're compiling this and like giving this as our kind of top level source file, this acts like main. But this thing down here is like the same kind of an object. So like we're creating a function here, basically, we're creating a module. And down here we're using an instance of a module that the library has defined. So the standard library for this chip basically knows how to instantiate one of these modules that links up to a physical thing that exists on these chips. So this is how we're effectively using a resource that exists physically, which is what we're always doing with an FPGA. We're never like instantiating a brand new thing. We're always just connecting things that exist. But some things are special, and there might be an especially limited number of them. So like clock multipliers or memory blocks. Sometimes there are special hardware units that just do like binary multiplication, or there are hardware units that are an entire CPU. So we're setting this thing up to act as a ×5 multiplier that is suited for this particular frequency range. So it's good for 30 megahertz in and 150 megahertz out. And we're wiring it up using these, which kind of act like the parameters we're passing to a function in a programming language. These are sort of like what wires we're attaching to the module. And it's kind of like, it's kind of like these parameters up here. The data types here could be single wires that could be inputs or outputs or bidirectional. They could be like arrays of wires that can be treated like numbers. And so here we're wiring up some of the signals. We're saying that the reference clock we're using as input, the thing that we're multiplying, is the clock that we're getting from Chip Whisperer. So we're just wiring that directly to the input up here. There's nothing in between there. It's just interconnect. And then the output is going to this internal signal called IF clock, which is just going to be like a temporary wire. And I'm actually noticing that normally I would write that with an explicit wire declaration. I guess it doesn't complain if I don't, but it's probably good practice to declare that wire. And so that's just saying like this is a single bit electrical signal. And you could use that for data purposes, or you could use that as actually a clock that drives other logic. So in this case, we're actually using this signal as the edge that causes other logic to make progress. So in this case, that intermediate frequency clock, which is our 150 megahertz, is actually driving this divider circuit. So every time that 150 megahertz clock experiences a positive edge, the logic inside this clause runs. And when I say run, it means that what's actually happening here electrically is this is building a circuit where this counter has a pathway routing a signal that's being computed as that counter -1. And it also has a path where it's being routed to this other value where we're taking a constant and setting it to the counter. And so what that actually does is it creates kind of a decision circuit where this counter always gets some input on every clock cycle, but depending on the value of this calculation, so whether or not the counter is 0, it will either assign it a value based on this path, or it'll assign it a value based on that path. But on every clock cycle, something's got to happen. And if you don't assign a value specifically, then it's implied that it takes the old value. But for example, you couldn't assign both of these on the same clock cycle. That would just, that would either generate an error or just be kind of useless code, depending on how smart your synthesizer is. So in this case, this is kind of idiomatic. Like we're writing this expression that you can read a little bit like a programming language, but with this knowledge that everything happens simultaneously. So we're saying that on each of these positive edges, so everything in here, this all happens 150 times, or 150 million times a second. All of this runs, with no exceptions, always happens. And if the clock's previous value, so when we're referring to this, this is always the value it had on the last clock cycle. And when we're writing to it, it's always the value it has on the next clock cycle. So here we're just saying, if this clock is about to overflow, then we're going to reinitialize it using this kind of pre-calculated divisor value. And at the same time, we're going to toggle this other value that's stored in a separate register. But if it's not about to underflow, then we can go ahead and subtract 1, and we don't do the toggle. And because we're not setting this value in this path, it's implied that it's the unchanged, so it doesn't have that toggle. It's just the same as if we had said output clock, arrow, output clock. So as a result, this is a simple clock divider. It ends up counting down from this preset value, this divisor, until it hits 0, and then when it hits 0, it toggles this other value, output clock, and then it just keeps doing that. And so that runs simultaneously with this thing up here. So while this is getting the clock from the Chip Whisperer and multiplying it up from 50 to 150 megahertz, this thing down here is taking the 150 megahertz clock and dividing it down again by this weird number 24 to get the 6 1/4 megahertz clock that we want. And then just some more wiring again, we can just take that output clock and just connect it directly to both of those output pins. And so that'll cause interconnect to be generated, like buffers and wires, but no combinatorial logic. And then just, this totally is unnecessary, but I wanted a bit of an indicator that my clock is ticking away happily. So this is generating, I can actually get this on the camera in the corner. This is generating a little bit of LED bling. Which is conveniently under the Ethernet cable. Yeah, sure. So you can tell that that's clocked by this pin. If you just pull that out, you can watch it stop, and you can put the clock back in, and it keeps going. Not a lot of chips like having their clock stop like that, but sometimes this one's fine with that. Sometimes the PLL loses lock. Currently, the way I reset the PLL is to just reset the whole Fpga. Might be easier to focus if I made that bigger. Oh, I turned off Synergy, but I don't have keyboard focus in the thing that lets me change channels. Yeah, I do need to make maybe a dedicated button instead of this thing that relies on the keyboard focus. Something with a weird keyboard combination that I can have OBS trap directly. That would be nice. Oh, that's why I can't focus. It's a little too close. There we go. Yeah. It's not the prettiest light show, but it tells me the clock's ticking. So yeah, that's just 2 bits from a binary counter, and then those same 2 bits inverted on 4 LEDs. And then the middle LED is just wired up to the PLL lock signal. So let's go back to the computer. So this is going to look a lot like the other thing, except now we're using yet another clock. FPGAs are really optimized to not use a lot of different clocks because, even though you typically can use any signal as a clock, they usually have a special distribution network that can handle, taking maybe a couple of clocks or maybe 4 clocks and getting them all over the chip, just giving them a way to go to every single flip-flop, every logic element in the whole chip. But and so in a design like this, maybe the optimizer decides like, oh, this thing, you use it as a clock once. I'm going to assign it to a global clock buffer. But usually that's not what would happen, and this would just be this wouldn't necessarily be the most high performance way to use clocks. You would usually want to stick to, a smaller number of clocks and perhaps have, like a high-speed clock that does something really quickly and then stops, goes back to sleep. But in this case, we are just using this FPGA as kind of a PLL and a divider. So yeah, these assignments are nice too. These just create, so like whereas these always statements with the with the arrow here, these imply a flip-flop. So like a logic element that stores a value and then like holds on to it so that the next clock cycle can use it to compute another version of it and so on. These assignments don't include any storage. They're just wiring. But when you wire things together, you can also do calculations. And this is combinatorial logic. So in this case, it's simple, it's just an invert, so I'm just using the opposite value here. But you can actually do fairly complicated things without even having to store intermediate values. That just limits the maximum clock speed your design can run at, because the clock speed is often limited by what is the one most complicated thing that you have to do between clock ticks. Well, that's the shortest you can make those clock ticks. So that's a really good motivation to split things up into smaller stages, like pipelining. So it looks like in this architecture, and I mean, I've got some vague memories of going through the official documentation on this. And I mean, I think they even mentioned this in the iStorm project webpage, that if you really want to know what's in the Fpga, probably the first thing to start with is the official documentation, because they do actually talk quite a bit about the architecture. And I think that this tile layout is actually specified in the official Lattice Fpga doc. But the main kind of secret here was inside one of these. Well, now the reverse engineering effort has led to this amazing chart where it looks like there's some unused bits, but then you also have details for which bits are being used for which parts of the logic operation, and this all kind of turns into a database that is both intended to be human readable for the reverse engineers at least, but also used by the automated tools like that Arachne place and route. Yeah, I really like this open toolchain, and I'm sure that it's got some limitations still as compared to a full-size kind of full-strength, full-size whatever SDK. But I mean, last time I was doing kind of some serious development with this SDK, there was no timing analysis tool, for example. You just had to kind of hope your design would run fast enough. Because that's like, FPGAs, if you're not familiar, have a totally different failure mode than a CPU. But if your code doesn't run fast enough on a FPGA, then it's like the data doesn't get there by the time the next clock cycle happens. And that clock cycle is still happening. So your data is just going to be corrupted. And so that's a big part of your job in designing hardware, is to make sure that that never happens. Or at least as close to never as you can do within the limits of physics, which is pretty close. And it's a bit of a rabbit hole for this particular stream. The kind of big picture here is more of a glitching setup, but I needed a way of doing some clock synthesis for the glitching, and of course FPGAs are pretty great at that. So so the thing that I had handy was this ICEstick, which is a cheap dev board with the ICE40 FPGA, and then this open source ICOTC toolchain, which is Yosis plus Arachne place and route plus the what is it called? ICO tools, or I think it's just ICEstorm. Yeah. Anyway, it's the names are still kind of a mouthful. I think they're trying to kind of brand the overall toolchain as ICOTC or ICOTC. But then each of the individual pieces are still projects. So it's like the kind of standard problem you have with Linux and a lot of open source stuff, where identity and convenience are sometimes at odds. But it's good stuff. And I think most of it's GPL licensed, or no, most of it's BSD actually. Arachne place and route I think is GPL, but then I think the other two pieces are BSD or something like that. A couple of us I think have asked whether the Arachne place and route developer would relicense with something that isn't GPL, so I don't know if that's going to happen, but some of us are asking. Not like I want I don't know, I think most of the reason why I don't know. I used to like the GPL, I guess, and I guess the reason I used to like the GPL is I don't know. I don't know if I'd actually thought about it that much. It seemed like kind of the default license for a lot of things, and I think to some extent I liked the idea of kind of contributing to this shared base of code that benefited open source, but didn't necessarily benefit anyone who didn't play by that particular open source rule set. I don't know, and I liked that for a while, but then I guess I just started to see more and more of the ways that the GPL got in the way and just kind of scared off people from contributing or using the project. and I had a hard time seeing it being a super helpful thing, except for maybe Linux. Like maybe Linux is better because of the GPL. Maybe some other like very large projects that you don't want to just kind of get wholesale pilfered. But for a lot of projects, it just seems like it ends up being much more of an encumbrance than a kind of safety net for those projects. Yeah, I'm really interested in doing things with Fpga tools that the commercial tools don't make easy. And I was wanting this for a long time, and even very briefly started to think about doing reverse engineering on my own with some small Xilinx Fpgas. I think I wanted to do something with like partial reconfiguration and genetic algorithms that would have been really annoying on like a Xilinx platform. Some of you have probably heard of this pretty famous genetic algorithms experiment with some Fpgas that are pretty old at the time, but they were kind of evolving this to find a circuit that was a frequency detector. So you'd give it a square wave at one frequency and it would say yay, and it would say nay for other frequencies. And the kind of famously surprising result is that their algorithm ended up creating some circuits that satisfied the criteria, but only because of kind of electrically unintended consequences in the Fpga, so stuff that didn't appear to be connected but was causing like parasitic effects, or and there are so many ways that could happen, you know, via capacitive coupling or coupling through the power supplies. So that's pretty interesting, and that definitely sparked my interest in, you know, maybe not achieving those same results, but at least trying to do some research on algorithmically generated circuits. And part of the problem is, you know, if you want to generate the circuit at like a Verilog level or something, then you're spending lots of time running the synthesis tools. Whereas if you want to generate the circuit at the bitstream level and just kind of permute the connections between components, that's what they were doing in this old study, but that only worked because the Fpga involved was so old, and because of its very particular architecture, it wasn't actually possible to damage it by just randomly connecting things. Whereas in any modern Fpga, that's not true. Like, it's easy to damage them, and the bitstream is, you know, much harder to modify in a useful way. So yeah, I think it would be interesting. And I'm already noticing some stuff where, yeah, that like maybe there are some open source uses for an Fpga that is configurable from, you know, like an ARM platform without a lot of memory, and like partially reconfigurable at runtime with, you know, different bits that might be connected differently. All right, so ICEstick is compiled and installed even. Yay. Can we make? All right, that's it. So we made it, and so that generated all the little intermediate steps. So now I can take a look at what's going on. This will answer some of these hypothetical questions. So we've got a bunch of these outputs. So I think the first thing here, we converted the clockgen.v into clockgen.blif, which is the kind of logic netlist format. So you could there's probably some program out there that will turn this into a schematic, like a graphical schematic with nice wires and everything. But that's the information this contains. It has the same kind of hierarchy model that Verilog uses with, you know, you've got like a block that we're calling top, and it's got these inputs and outputs. And then inside, it's just instantiating a bunch of other stuff. So we have these gates. You know, instead of AND gates and OR gates and things, we'll usually find these lookup tables with 4 inputs, which are the kind of basic building block this Fpga uses. So then it says here's where the inputs are connected, and this is like an encoded representation of the function. Or no, that's not what that is. Where is the function? Oh, this is the function. That let init prim is the actual function that goes into the lookup table, and then this mess is actually just a temporary variable name. So, like that's probably just called ABC because maybe that was the program that generated it. And then this is probably just like a number that increments. So this is actually implementing a digital counter. We've got a bunch of these lookup tables, then there are some general purpose, the lookup tables are the general purpose logic, but then we can also see some special purpose logic, like this is just for a carry chain in an adder. And then these things are flip-flops, so each of these stores 1 bit. This is the basic element of the kind of memory that gets built into logic. It keeps track of a bit as it's flowing through a logic circuit. And these are the parameters for the PLL that just go into some very device-specific stuff to get encoded to the hardware's format. So that's all we got in the BLIF file. And then I think the next step is that gets placed and routed, and then that turns into this ASCII representation of the format that's actually in the FPGA. So a bunch of 1s and 0s in really apparently no particular order, even though there's some very complicated relationships that explain how these work together. And then there's the binary file, which probably isn't super interesting, but is basically just those 1s and 0s plus a header and a footer, I think. Mostly 0s, because this FPGA is mostly empty. And then the .rpt file is, I think, a timing report. Yeah. So this goes back and takes the design after we've already converted it into the closest representation we have to the hardware. Now it goes back and figures out how long will all the kind of longest operations in here take. So this is actually telling us, I think this one on top is the longest. So this path, it would take some work to figure out what it actually means by this, because it's talking about a bunch of names which were generated by the compiler from this top level thing. It's kind of the equivalent of like attaching a debugger to something and seeing, you know, the name of some temporary variable that the compiler would have emitted into the assembly code. But then it tells you actually this path took 640 nanoseconds, and so that's limiting how fast this particular clock can tick. So that's basically it. And the nice thing about this is all open source and you can read it all. So, and the upshot if you're actually reading this file is this tells you how fast the slowest circuit is limiting you to. So once we've got that, we have this program ICEprog that actually takes that binary file and copies it to the FPGA. And because this particular board I modified to load directly into SRAM, I have this parameter. Oh. There we go. And now you can see in the little picture-on-picture window that the LEDs are happily blinking away. This program's pretty fast. Like, that's just the time it takes to copy 32 kilobytes over SPI into SRAM and then reset this thing a couple times. So, dynamic logic. If you haven't played with it, I would recommend it. It's fun to get into, and the tools and the hardware are way less annoying than they used to be.